welcome everybody to this session on interacting particle systems of the Mathematical Conference of the Americas. Just a quick announcement. Unfortunately, we had to cancel the last talk of today by Jonathan Ehrman. So that means that we are going to end a little bit earlier, but the program will stay the same regardless. Okay, so let me introduce now Daniel Valesin. It's always a pleasure to introduce Daniel, a longtime friend and also a great Brazilian mathematician from University of Groningen. So he's going to talk about the contact process on random hyperbolic graphs.
Okay, thank you very much, Milton, for the introduction. And I'd like to start by thanking the organizers for inviting me. It's an honor to be invited to this very nice session. And I'll speak about some joint work with these people here. So Amitai Linker, who is in Cologne now, I think, Dieter Missia, who is in Lyon, and Bruno Shapira, who is in Marseille. So it's about a contact process on a class of random graphs called the random hyperbolic graph. So I guess most of the audience knows about the contact process, so I'll go over it quite fast, and then I'll spend some more time talking about the graph because maybe it's a bit less familiar. So here's a brief summary about what I'll need for the contact process. So we start with a graph G. Let's say it's a locally finite graph, and then we define a process psi t, which is a continuous time Markov process on this state space 0, 1 to the power of the vertices of the graph. So 0 meaning healthy, 1 meaning infected, and then there is this parameter lambda larger than 0, which is called the infection rate of the process, and the dynamics is described by these rules here. So if you have a configuration psi in 0, 1 to the v, and you have a site x or a vertex x, then there are two types of jump. You can jump from infected to healthy spontaneously with rate 1, and you can jump from healthy to infected with a rate that is given by lambda times the number of infected neighbors, so the number of vertices y neighboring x, so that y is in state 1 infected. And we adopt this usual notation where we write a superscript indicating the set of vertices that is. So here A is the set of vertices that is infected at time 0. And we also write. So here I'll write 0 with an underline for the configuration, so it's 0, 1 to the v, for the configuration of where everybody's healthy, and this configuration is of course an absorbing state for the dynamics. So at any point in time everybody's healthy, then the system stays that way. And one easy observation is that if you're running the process on a finite graph, then this state, all healthy state, is reached with probability 1. And then we can define a random variable tau g, in fact, the stopping time for the dynamics. And this is the first time at which this all healthy configuration is reached. So here in the definition of this random variable extinction time, I set the initially everybody's infected. So I started dynamics with everybody infected time 0, and then I wait until the infection is gone. So that's a stopping time called the extinction time of the infection, and it's almost surely finite if the graph is finite. On infinite graphs, well, there are situations where it can be infinite. Then I'll very briefly discuss what is understood by metastability in the context of the contact process. So the framework to study metastability in the contact process is that we fix a value of the infection rate lambda, and we take a sequence of graphs Gn, which is typically from some natural sequence of graphs, for example, boxes of ZD or random graphs coming from a common random graph model, something like that. But let's say we have Gn, and with number of vertices going to infinity, And then as we're growing the graph, we study how this random variable behaves. So its growth, let's say the growth of its expectation or its behavior when you take n. And so study tau gn, especially as n goes to infinity. And this is, you have to emphasize it's for fixed lambda. So we don't vary lambda as we're varying n. I mean, we could, but typically we don't. And here's an example where many things are very well understood. So so in the case where Gn are this lattice box, so one box of ZG with side length n, then there is this change of behavior. So that there is this critical value of the infection rate, lambda c. And by the way, for people who know, this is of course the same as lambda c of the infinite volume contact process, but I haven't defined that here, but never mind that. But there exists this critical value, so that if lambda is smaller than lambda c, then the extinction time of the infection grows logarithmically with the volume of the graph. Whereas if lambda is above lambda c, then it actually grows exponentially with the volume of the graph. So there are some references here. I didn't. So this is Duret Liu 86. This is Cassandro Galvis, Olivieri, and Varis 84. Then Schoman 85, Duret and Schoman 88, and Mumford 93. So this result here was proved in several steps, starting with dimension 1 and lambda large enough, and culminating in well, the full result on ZD with any supercritical lambda. And this second case here, is case lambda larger than lambda c, is what is called the metastable regime, because the system stays for a long time in this fake equilibrium state in which the infection is active until it reaches the actual equilibrium state, which is the absence of infection. By the way, this result for lambda equal to lambda c is largely not open, so it's not well known what happens if you take lambda equal to lambda c. I think so. There are only results in dimension 1, and they're not sharp. So it's just known that lambda c grows within 2 polynomials of n, but the precise behavior is not known. This was for boxes of ZG. So very brief introduction to this. Well, this is what is called a finite volume phase transition, because it's a phase transition that manifests itself already in the modern finite graphs. Well, people studying the contact process around the 2000s, there was sort of a shift of interest, or at least interest. People started to be interested in the contact process on random graphs, or more general classes of graphs. And there was this, I don't know, let me call it this discovery, or this message that on scale-free graphs, meaning graphs in which you have vertices of high degree, or the degree distribution is a power law, so you have a very, very well-connected vertices, that on such vertices, lambda c is 0. And when I say here lambda c is 0, what I'm actually trying to say is that this first regime here doesn't exist for those graphs. So that somehow, if you take lambda larger than 0, no matter how small, still this extinction time will grow very rapidly with the graph, and typically exponentially with the number of vertices of the graph. And the reason for that is well, sort of outlined here, that if you have vertices of high degree, so let's say this is what is called a star, or a super spreader, I guess some people call it, but it's a vertex of degree d with d large. And the point is that these vertices hold the infection for a very long time, because you know, the center, if the center gets infected, it transmits the infection to many neighbors, and then the infection keeps coming back to the center. So the center keeps more or less all the time being infected, because as soon as it recovers, it receives the infection again. So this star alone, without even without the help of the rest of the graph, this star holds the process, the infection for a time that is exponential of constant lambda squared times the degree of the star. So that means that if d is much larger than 1 over lambda squared, then this time is very big. So this is the relevant size of a star. If you fix lambda, then this is what decides what is a star for the point of view of the contact process. And now, if you have a graph, so let's say if you have a graph Gn, which is a power law random graph, and so remember, we're fixing lambda and we're taking n to infinity. So if you take n large enough, eventually you will see some of these stars appear. So some of these vertices that are much larger than 1 over lambda squared. And in fact, you will see order n of them. So it's well, a constant depending on lambda times n. That's how many of them you typically see. And well, in many cases, you can also guarantee that these stars are not very far from each other. So that even if the infection is taking place in each of them, and even if it happens that this star manages to recover from the infection, then the infection coming from this other star comes back. So you have a sort of coarse-grained contact process that takes place on these stars alone, and that's a mechanism that sustains the infection for a long time. So that was the sort of mechanism that people started investigating, and originally, at first in the preferential attachment graph. I think that was the first instance where something like this was proved, but then in I guess the point that really made people interested in this was a paper by Chatterjee and Durrett, which sort of disproved earlier conjectures by physicists. So for physicists, there was in the physics literature that they were studying the contact process on the configuration model with power law degree distribution, and they predicted. So there were some papers predicting actually a phase transition, like the one I showed here for boxes of the D. And there were several papers, so some of them doing some numerics on estimating the critical value and so on. But then there was this paper by Chatterjee and Durrett that proved that in fact this regime didn't exist at all, so that the process was always metastable. But okay, so this was the preliminary things I wanted to say about the contact process. Now I'll say a little bit about random hyperbolic graph. This is kind of a sentence to say what it's about. It's about continuum percolation, meaning percolation between nodes of a Poisson point process, but in a setting that is not given by Euclidean geometry, but it's given by hyperbolic geometry. And this is a random graph model that's being introduced by these people. So I had to write down their names: Kryukov, Papadopoulos, Kitsak, Badat, and Bogunia. Something like maybe 12 years ago, if I'm not mistaken. And sort of the highlight of this graph is that it's sort of a natural definition. So it's a model that you define in hyperbolic geometry, and it naturally captures these sort of these three features that you observe in real world networks, or they're desirable to have in models of the real world networks. So small world, meaning small diameter; scale free, meaning power law degree distribution; and clustering, meaning that locally you see triangles. So the graph is not locally tree-like. So I will talk about, and by the way, this is a model that is defined in hyperbolic geometry. I'm not a hyperbolic geometry person. I just look at this graph and I take it as a random graph with funny distance formulas that are supposed to mean something, but I don't know what they mean. So I just take it as a given. And I'll present it in this spirit. So here are the two parameters that we will use. So n will be the number of vertices, or actually the expected number of vertices, because the number of vertices will be random. And there will be a parameter alpha larger than 0, which together with lambda is the second parameter that you have to remember in this talk. And I'll tell you in a second what this is. So to define the model, you do the following. You take a disk, so just an Euclidean disk in R2, a disk with this radius 2 log n, and the points of the disk I will denote the points with polar coordinates, so r and theta, with little r between 0 and big R. And then I take the set of vertices of the graph, will be this Vn. So this will be a Poisson point process on the disk, but it has a certain intensity function with respect to Lebesgue measure. So it's not so it's a Poisson process with intensity function given by this. So this is the intensity function with respect to the Lebesgue measure. So what this intensity function is doing is just, so this is just a normalizing constant in front, which depends on alpha and n. But then you just take a hyperbolic sine of the parameter alpha times r. So so this is, of course, so hyperbolic sine is growing exponentially like this. So it's what this is doing is that it's favoring a lot vertices that are far from the center, that are closer to the boundary. So the closer to the boundary, you have exponentially more points than near the center. So that's all that is. And the choice of these of this constant alpha n here is just so that that this integral of g. So if you integrate the intensity function, you get the expected number of points, and you choose the normalizing constant just to get n points on average. So just to have n nodes in your graph. And then, as I said already, this parameter alpha controls the concentration of points near the boundary. So if you take alpha equal to 0, then the measure that you get is just uniform on the disk without any. So just Lebesgue measure on the disk multiplied by the n, so that you have n points on average. Whereas if you take alpha to infinity, then you have barely any points. So the limiting case is when all the points are uniformly distributed on the circumference, and none of them are in the interior of the disk. Oh, I forgot to say, of course, this measure is radially symmetric, so there's no so there's rotationally symmetric. Now we've defined the set of vertices of the graph. I haven't said now how you define edges, and to define the edges, I have to give this ugly formula from hyperbolic geometry. So when you have two vertices, u and u prime in your graph, you put an edge between them if this the distance is smaller than or equal to r. And so this number r, 2 log n, this number r is actually playing two roles in the story. So originally r was the radius of the disk that I took. So r was the size of the disk, but it also serves as a threshold to decide when I connect two vertices with an edge. So I connect two vertices with an edge if they are r close to each other in this distance, and this distance is given by this ugly formula. By the way, it's given implicitly, so it's given by an inverse hyperbolic cosine of these of doing this operation. So just to give you maybe I should start another. Let me start another document just to draw a picture. So what this does is that if you, so here's our disk of radius r, which is 2 log n. So if the Poisson process, if the process of vertices happened to have a node right in the center of the disk, then this node, the ball with radius r centered at this very node would just be everything. So if the Poisson process happened to have a vertex in the very center, then this vertex would be connected to everyone in the graph. But then if you have a vertex that is, let's say, here near the boundary, then the ball of radius r around it looks sort of like this. It looks like very, very tiny nearby. So this is the region where it's connected to other nodes. So if you have a node right here, it will be connected to other nodes in this region that I drew, but not outside it. So the effect of that is that, the vertices of the boundary, they are connected to other vertices of the boundary very nearby. But of course, if there is someone near the center, then it tends to be connected to most of the people. And that's kind of, oh, now how do I go back? So let me see, yeah, here. So this kind of explains this little simulation that I'm showing here, why you get this sort of picture. So you see, you get exactly what I said. You get, well, some high concentration of vertices near the boundary. But there are some very few near the center, but they are very well connected. That's the philosophy of how you should understand this graph. So so some things that are known about this graph, and I should speed up a little bit, I see. Some things that are known about this graph is that the degree distribution is given by a power law with exponent 2 alpha plus 1. So alpha is this parameter that I mentioned, which is positive. So the power law with exponent 2 alpha plus 1, meaning this, that the probability. So if you take a vertex u, so u here is uniformly at random. You choose a vertex uniformly at random, and you look at the probability that its degree is around k, and that probability will be around, so modulo constants will be about around k to the power minus 2 alpha plus 1. So I think this result was already proved in the paper that introduced the model, but if I'm not, I could be wrong there. But here are some other things that are known about this model. So this axis here is the parameter alpha, which is anything positive. So here the idea is that you're fixing alpha and you're taking n to infinity. And there are different regimes. So if alpha is between 0 and a half, then the degrees, the expected degree is the expectation of the degree is infinite, and the graph is connected with high probability. If alpha is between a half and 1, then that's the regime where you have a unique linear sized component. So you have a unique component of size of order n, and all other components are sublinear. By the way, these things are proved by this paper. This is Bode, Fontolakis, and Müller 15, and Fontolakis and Müller 18. Whereas if alpha is larger than 1, then you have a regime where the components are all sublinear in size. So that's I will, for the rest of the talk, I will focus on this intermediate regime where alpha is between a half and 1. And the point of that is that, you know, I'm interested in running the contact process on this graph, and so I will care more about the case where I have a linear size component. So that discards this upper regime here, because then there are no linear size components. And moreover, yeah.
So I was expecting that the larger the alpha, like the more connected you are, but it seems that that's wrong, right?
No, the larger the alpha, that means that the tail of the degree distribution is lighter, right? So that means that so you can imagine a large alpha, yeah.
Sorry. Okay, thank you.
Yeah, sure. And yeah, I discard. So I will not look at this upper regime here because I want to have a linear size component. I could look at this lower regime, and in fact that should be done. But we haven't. So because we wanted to have finite expectation of the degree distribution. So we discarded this one. So I'll focus for the results I'll present. I'll focus on this intermediate regime. So so alpha is between a half and 1 for the rest of what I'm saying. And well, the plan is to fix the parameter lambda of the contact process, and then run the contact process on the graph Gn. And of course, we're in this intermediate regime, so Gn has one linear size component and then some smaller components. You can just think about the contact process on the linear size component, because the other ones are much smaller, and you can ignore that. So okay, this is the setup. Is there anything I can clarify about the setup, because I announced the results now? So for the results, I just reminding you here that that tau of Gn denotes the extinction time of the contact process, and the first result is I'm calling it persistence. I could call it also metastability. So this is the result that if you take lambda larger than 0, and you take alpha between a half and 1, as I said, then there is some constant c and some positive beta, so that the probability that the extinction time is more than e to the power of cn. This is a annealed probability, by the way. This is the graph and the process. So this probability is 1 minus a stretched exponential function of n. So we also show in the paper that you can't really improve, you can't get exponential here, because you can pay a price of a stretched exponential order to make the graph behave in a certain way so that the infection doesn't survive that long. But anyway, but yeah, with outside this probability, then the extinction time is indeed exponential. And I won't comment too much about the proof of this persistence theorem, because it's more or less what I already said in the beginning. So you just have the graph, you just find this network of stars, you need order n of them, and they need to be kind of close to each other. And then there are some general results that say, so this one I won't comment too much about the proof, but yeah, so you also get metastability for any value of the infection rate. So the second result is about density. So it has an ugly statement. I'll go over it in detail. I guess almost running out of time, but I want to state the theorem properly. So again,
sorry, another question.
Yeah.
This is about intuition. So in this model, the nodes with large TE are those which are closer to the center, right?
That's exactly right. Yes, okay. Yes, the ones in the near the center. Yeah, if there is one, if there happens, I mean, it doesn't happen, but if you had a vertex exactly at the center, so its degree would be, everybody would be connected to it. Yeah. And I think that was something guiding the intuition of the people who introduced this model, that somehow they thought that real world networks should have a geometry, kind of hierarchical structure behind them. And if they have such a hierarchical structure, this structure should be more like hyperbolic geometry than Euclidean geometry. So I guess that's what it was. But because of exponential growth and this kind of thing. But okay, so the density theorem goes as follows. Again, any lambda larger than 0. And but for this theorem, you should actually think about lambda 0 to 1. The statement lambda small, actually. The statement will be kind of trivial for lambda large of this theorem. And again, for alpha in this intermediate regime of the graph, then there exists a constant such that the following thing holds. So I take a sequence of times, Tn. So Tn is a sequence of times that is going to infinity, but much smaller than so this constant C here, you can think of it as this constant C of theorem 1. So this C, this is like the extinction time. The point is that this sequence Tn should be growing, but much slower than the extinction time of the infection. So it's a typical time of activity of the infection in the nth graph. So you should think of this Tn as a typical time of activity, and then you do the following thing. You just take a snapshot of the process at this time Tn. So this is a probability for the process on the graph Tn. Then this quantity that is appearing here is the density of infection. So it's the number of infected individuals in the graph Gn at this typical time Tn, and then divided by n. So that gives you a density. So the density of infection. And the claim is that there is a certain function of lambda that I'm calling gamma of lambda here, so that this random density is very close to this deterministic function of lambda. So the probability that they're epsilon far from each other goes to 0 as n goes to infinity. And this function gamma of lambda, we know what it looks like for lambda small. So we know when you take lambda to 0, it has a shift of behavior in this value of alpha equal to 3/4. So for alpha between 1/2 and 3/4, this density function behaves like lambda to the power of 1 over 2 minus 2 alpha. And for alpha here it behaves differently. So there's this exponent and there's this log correction. And well, this meaning of this symbol is of course that it's within two constants of this asymptotic value. So yeah, maybe do I have something like 2 minutes?
Yeah, you have 2 minutes. Yeah.
Okay. So let me say something about these results. So the first thing is that we have a previous paper about the contact process on the configuration model with power law degree distribution by Mumford, myself, and Yao. And let me just say that we get there the same results, and in this density theorem we get the same exponents. So these exponents, they look like they could be present in other classes of random graph as well. Regarding the proofs, this is a remark. So as I said, we already knew the results in the configuration model. The configuration model is locally tree-like. The graph that I'm talking about here is not locally tree-like, so there is clustering. The clustering doesn't change the results, but it makes the proofs a lot harder, because then there are some martingale techniques that break down. Let me not get into that. For the proof of the persistence theorem, I already mentioned that we find a subgraph of stars and for the density theorem, so there is a sketch of proof here, which I was too optimistic with thinking that I would explain this. Let me just mention that we reduce the problem of studying this density to the problem of studying the survival probability of the contact process on an infinite graph. So there is a local limit. So this is the local graph limit of this. So you see, this is the little window in the random graph, and this is like a local limit, which is in the upper half plane. And then you just study the survival probability of the contact process started from a certain vertex in this limiting graph. And the result and the study has a flavor of large deviation theory, because somehow, you know, since lambda is small, you have to capture the best strategy for the infection to survive. This strategy involves both the behavior of the graph in this around this random root and the infection. And yeah, when you find these different strategies, that gives rise to these different regimes. But okay, so I'm out of time. I was too optimistic with showing that yeah. But so I'll stop here. Thank you.
Okay, thank you very much, Daniel. So let's thank Daniel for this nice talk. So do we have? I think I have time for one or two quick questions. Yes, Elena.
Well, I wanted to ask about 3/4. Any intuition behind 3/4?
So I don't have a quick answer of the type. That's when the second moment or anything quick like that. So what I had planned to show is that there are some you find some different strategies for the infection to survive. Mm-hmm. The infections are all of the kind, you know, here's the root. The root has a big neighbor, and this big neighbor does something. And then what this big neighbor does is one thing in one of the strategies, and it's something else in the other strategy. And these two strategies, they are valid regardless of alpha, but for some values of alpha, strategy 1 is better, and for other values of alpha, strategy 2 is better. So when you find these 3/4 is something along the following lines. When you find a big vertex, you want to count how many neighbors. So when you find this guy U star, you want to find how many neighbors of U star that are even bigger degree than U star itself. So that has to do with the tail of the degree distribution, or rather the size bias degree distribution, but it's the tail of that. And that then you do a certain computation, and that's where the 3/4 appear. So that's kind of the best answer I can give. So you write a little equation. So this is like the degree that you need for this U star in one of the regimes, and this is in the other. And the 3/4 is when the two things equate. Yeah, that's sort of the way I see it.
Thank you. But on phenomenological sort of,
yeah,
there isn't much you can say that, oh, it's that.
No, yeah, not in terms of a very clear change in the yeah. So I would say it's phenomenological.
Okay.
Thanks.
So,
thanks.
Any other questions? Ines, wanted to ask something? Yes, Ines.
Yeah, I mean, you have these results for discrete values of t. Do you have any intuition what happens if you look at all times?
So this is when you fix. So I guess this sequence Tn here, right?
Yeah.
So well, this theorem is true for any sequence Tn that you fix that satisfies these properties. Maybe so you could also, another thing you could do is that you could take, because you see here, as we change the process, we also change the time. You could fix a value of n and then look at the process for different times at this n, and then well, we haven't proved anything about that, but it's true that contact process, typically the mix is very fast. So if you take this several times that are sufficiently spaced from each other, then typically you will see this density in yeah, if you take finitely many of them, you will see this density in all of them. So there are things like that you could do. Well, of course, something that is much harder is to study, well, the behavior of this density for fixed n as a stochastic process and study the fluctuations. That we haven't done at all, and that I guess is much harder.
Okay, very good. So if there are no more questions, let's thank Daniel again for his nice talk.
Thank you very much. Pleasure.
So now we'll just do